Today we're going to do electric potential energy, voltage, and capacitance. Potential energy is fundamentally an energy of position relative to some force. Gravitational potential energy answers the question, is there room to fall? Relative to what? Relative to gravity. Electric potential energy answers the question, is there room to zoom? Relative to what? Relative to the electric field. If we want to set up a formula for electric potential energy, we can try our luck making something parallel to what we have with gravitational potential energy. Gravitational potential energy locally was good old mgh, where mg was the force of gravity and h was room to fall. Similarly, our electric potential energy should be some kind of electrostatic force, attraction or repulsion, and room to fall, or horizontally, room to zoom around. Our force, based on what we learned yesterday about electric field, will be the product of the electric charge and the electric field times the distance to zoom. So there we have it, a nice formula for electric potential energy. Why negative? Unlike gravity, which always attracts two masses, electricity can both attract, positive, and repel, negative. This is really a hand-waving argument because the real setup for electric potential energy takes into account the fact that E, the electric field, is not necessarily constant, not in magnitude, not in direction. The real definition for electric potential energy involves the calculus, making sure you're moving parallel to the electric field at all times, aka put your batteries in sideways, they won't work. Of course, when the electric field is constant, this, and this are the only thing that remains, and we get negative QED, just like the bird's eye view said we should. If our electric field E is KQ over R squared for 2-point charges, this gives us an extra Q and knocks out one of our R's for negative KQ Q over R. Note that in all cases, electric potential energy equals 0 only when the charges are infinitely far away from each other, aka they can't see each other and they won't react to each other. So, give it a try. How much electric potential energy, how many joules, is delivered from a lightning bolt of 5 coulombs traveling 2 kilometers from the ground? Figure it out. Pause the video and click again when you're ready. If you've got 3.0 times 10 to the 10th, that's 30 billion joules of electric potential energy, you are in good shape. Now, let's talk about electric potential, work, and energy. To talk about electric potential, the analogy I want to use is that of money. In the real world, we do work, and that work gives us money. We do $5 million worth of work, we get $5 million worth of money. We'll use this as an analogy for energy. We do 5 million joules worth of work, we'll get 5 million joules worth of energy. So, how far does $5 million go? Is it a lot? What about here at Rochelle Zell Jewish High School? Is $5 million a lot? Well, at a big school like Stevenson, $5 million is pocket change. To us, $5 million is a year's operating budget. We could all go to school here for free, bagels and all, for 1 year for $5 million. To us, $5 million is a lot. To Stevenson, meh, a month. A better measure of how much of a gift we have been given isn't dollars per se, it's dollars per student. Stevenson spells $12.7 million per student over the course of a year. Rochelle Zell spends $29.3 million per student over the course of the year, which is why, of course, you are here. The point isn't that the school gets a gift of $5 million, but we only have 160-something students to spend those $5 million on, whereas for Stevenson, the $5 million has to go among 4,000 students. Electric potential works the same way. We don't want to know just, oh boy, it's 30 billion joules of energy. We want how much energy per charge. How many electrons, how many electric charges do you have to spend those $30 billion on? If you have 30 billion charges and 30 billion joules of electric potential energy, that's not a lot of joules per coulomb of charge. But if you only have a couple of little charges to be using that 30 billion joules of energy, that's going to amount to quite a lot. Electric potential is electric potential energy per unit charge, and it's a much more useful concept than the pure electric potential energy. It's measured in joules per coulomb, electric potential energy per unit charge. This knocks out the charge you're working on and gives you the product of the electric field and the distance you move through it. More electric field, you'll have more electric potential. Move through the electric field, you'll change your electric potential, same way that going to a higher position would change your gravitational potential. Another name for electric potential, that is electric potential energy per unit charge, that is like how many dollars per student we have, or how much room to fall you have over a waterfall. Another name for that is voltage. When you think about voltage, you can think about charges flowing the way water flows on a waterfall. The analogy for electric potential for voltage would therefore be the height of the waterfall. Now, give it a try. Here's the spark plug problem. When we can solve the spark plug problem, we'll have learned everything there is for a first year to know about electricity and magnetism. Your spark plugs in your car have the simple and singular purpose of starting your car. A spark is needed to ignite the gasoline fumes in your engine chamber and start the combustion in your internal combustion engine. The spark is only there to start it off. Now the gap in between those spark plugs is 0.6 millimeters, the smallest humanly possible gap without running the risk that your spark plugs will touch each other. What voltage should your car battery need to apply to those spark plugs to make a spark? Pause the video, check your equations, figure it out, press play when you're done. If you got a voltage of 1800 volts, you did your algebra correctly, and herein lies the problem. Standard lead-acid car batteries, the biggest ones on the market, are 12-volt batteries. Nobody is going to build a battery with 1800 volts of voltage, and even if we did, it wouldn't be safe for the rest of us. How on earth are we going to transform 12 volts of battery voltage that we need to the 1800 volts that we need for the spark plugs? To be continued as we move forward in circuits, electricity, and magnetism. Capacitance is the way we measure storing electric charge, or to look at it from another perspective, storing electric potential. Capacitors store up electric potential energy by packing up uniform voltage and storing it on or in a charged surface. Uniform voltage means we need a uniform electric field, and as you guys figured out in your lab, the best setup for uniform electric field is found in between two parallel plates. Spheres also have capacitance. It's just not as easy to work with because the electric field isn't uniform. Capacitance is stored in coulombs per volt, electric charge per volt. 1 coulomb per volt is 1 farad of capacitance, which means we can expect normal capacitors in microfarads, nanofarads, and even picofarads because coulombs are so large. Check. The electric potential energy stored in 1 capacitor is equal to 1/2 QV squared, and given that this equation rearranges cross-solve to V equals Q over C, you can substitute it in and say that U, the electric potential energy stored in the capacitor, is Q squared over 2C. In general, a bigger surface means more charge, and that means more capacitance. Bigger parallel plates means that you need a bigger charge in order to affect the voltage. A bigger sphere means, again, you need a bigger charge in order to affect the voltage. That's why the Earth is the biggest capacitor we have. The surface is so big that you can discharge again and again and again all your excess electric charge without really affecting the voltage. Capacitors are all around us. They're there to charge up and then discharge their energy all at once in a blinding flash. Your camera flash is a capacitor. When you keep pressing the button and wondering why it's not taking a picture and the little light is going flashy, 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 it's saying, wait, the capacitor is charging up. Then the little light goes red, the capacitor is charged, you press the button, and all of that electric potential energy is released in a single blinding flash. Computer keys on a keyboard are also capacitors. By pressing the key, you are squishing the top plate closer toward the bottom plate. You're lowering the distance between them. This changes the capacitance, and this changes the coulombs per volt. The electrical signal the keyboard sends is a result of the changed voltage. Next unit, we'll start making circuits, and you'll see where in the circuits the capacitors will go, how we can charge them up, store the voltage we need, and discharge them when we want to.